Hello, welcome to this presentation of Razor Blades rotor systems. We'll try to cover every aspect of our manufacturing process so you can see just how far we strive to create nothing but the absolute best quality gyroplane rotor systems on the market today. We developed these blades not only for our own GT VX series gyro kits, but also to fill the need for smaller legacy gyros out there dating all the way back to the early Benson models. The blades are a bonded aluminum construction based around a NACA 8H12 profile with a nonlinear twist and reflex. We offer these in 23 to 27 foot diameter systems. We'll start this overview by looking at the internal components contained within each blade. Here's a section view to better visualize the assembly. We'll start with the extruded leading edge, which is the base component for the whole assembly, since everything else is bolted and bonded upon that. The machine end caps on the tip and the root are joined to the leading edge. Inside the back cavity of the extrusion, the tip weight is bolted and bonded. And here's the bolting insert on the root end. Then, of course, we have the top and the bottom skins made of 6061 T6.032 aluminum sheet. The joining straps consist of a set of aluminum inner spacers that are machined to match the profile of each blade. These are then sandwiched with a set of 80,000 psi steel backer plates for fatigue resistance. A lot of consideration has been given to stress distribution. The bolt and associated holes for holding the bolting insert in place is positioned way back in the clamped assembly. Then a generous distance is allowed between the end of the joining straps and the end of the bolting insert to help feather out the high stress areas. Our own custom extrusions are received in from the supplier and stored until ready for manufacturing. We outsource the cutting of the blanks for the top and bottom skins, the 3025 6061 T6 aluminum. We used to have these laser cut, but surprisingly we discovered it wasn't accurate enough. I guess due to the light weight of the material, the air blasts from the laser head, and small amount of heat distortion, it's just too easy for the material to move on the cutting bed of the laser and result in a out-of-spec blank. We now have the blanks punched to size, so that the CNC punch press is in complete control of the sheet until the final punch separates a blank from the rest of the sheet. All the blade components are machined in-house on our precision CNC equipment. Here you can see the profile shape that has been machined on both the bolting inserts and the tip weights. These will match the inside profile of the leading edge extrusion. The leading edge extrusions require a fair amount of machining to get them ready for acceptance of the other components. Shown here, we are machining them to length and adding some features that will accept the end caps. Here you can see the end prep finished on batch extrusions, awaiting transfer over to the blade room, assembly room, where they'll be stocked for various blade sizes. These end caps are very critical to the design of the blade system, as they are an integral part of the assembly, not just a cosmetic or a hole filler at the end of the blade itself. The way it's keyed, bolted, and bonded into the leading edge allows us to apply adhesive not only to the leading and trailing edge, but instead around the full perimeter of the blade, creating a very strong structure with high torsional stiffness. Vent, tracking, and balance weight adjustment holes are added to the end caps. The serial numbers are engraved in pairs to the end caps, marked with the X and O to show how they will be mounted to the hub bar. Here you can see the vent holes in this picture. And these holes here are for our coming soon CNC polishing system, which will precisely register the whole blades for that process. And here's a sample of how the end cap goes into the leading edge. You can see how it connects tightly. Once we get the adhesive in there and bolted in, it's integrated right into the leading edge. Now with that adhesive going around the full perimeter, we get a very strong bond and torsional stiffness. With the exception of the one sharp bend that produces a reflex on the trailing edge of the blade, the sheet metal is applied in the assembly in pretty much the flat state. The contoured clamps match the extrusion and hold the sheet in position to start the airfoil shape. And then, as the clamps close on the trailing edge, they direct the material into the 8H12 profile very nicely, giving a nice, wonderful end result here. The one problem area is the transfer from the extrusion to the front edge of the top skin. This is hard to get a smooth transfer without applying excessive amount of force to get the edge tucked down in there. And by applying excessive amount of force, a high pressure area would be created in this zone, which would push out much of the adhesive in this critical area. To remedy this, we create our own custom 12-foot long sheet metal brake. All parts were built in-house. In this picture here, you can see the two zones. This zone here is for doing the reflex on the back trailing edge of the top skin. And this zone here is for making that small tweak to the top skin to eliminate that high pressure zone I just mentioned and get that smooth transfer. Simple cycle, tweaks the part. Now that was the trailing edge being bent there, But here is the result of the other zone, which creates that little tweak that I mentioned was needed. It's a lot of work to address such a small little detail, but it's of the utmost importance to do it right in order to create a quality product. The etching process is absolutely critical to achieving a good, strong bond with the adhesive. We monitor the composition of the etching bath very closely, as well as keeping a large supply of fresh RO rinse water for post-etching cleaning. After the etching process, the aluminum will begin to oxidize right away as soon as it's exposed to the air, so we immediately perform a thorough force dry of the components and directly move on to the adhesive application. The adhesive we use is a 3M 163 2K heat-set epoxy. This is shipped to us via overnight delivery on dry ice, and in the package are digital recorders for monitoring the temperature during transit. Upon receiving it, we immediately transfer it to our freezer storage area and monitor the storage temperature very closely. The adhesive comes on a wide roll and needs to be converted into smaller strips for the blade assembly. It's removed from the freezer and allowed to thaw and slowly acclimate to room temperature as not to impose any condensation on the material once it's removed from its sealed packaging. I tried several ways to cut it down to size, all of which turned out to be slow and maybe rough edges and just not very accurate in general. So we designed and built our own conversion and slitting system just for this process. Now we get smooth, repetitive cuts exactly the width we need to use on the blades. The material is converted down into 3 sizes since the leading edge, trailing edge, and end caps all require different widths. Precise records are kept tracking every roll and lot of adhesive, including the out time from the freezer for each specific roll. The adhesive is applied to the components in a clean, sterile environment. Here you can see the adhesive being applied to one of the brass tip weights and then being inserted to the leading edge. It is then bolted into position and the bolts are torqued to specification. Once the internal components have in place, we can start on applying the adhesive for securing the top and the bottom skins. The adhesive is rolled to remove any trapped air bubbles before the backing material is removed from the adhesive and the skins are applied. A small amount of heat helps the initial attack before being transferred to the curing oven. All these components are tracked via lot numbers as well as the adhesive for every set of blades. At the same time, we produce a set of coupons. These are produced from the same lot of sheet metal, use the same lot of adhesive, and they were etched along with the blade components and cured in the same heat cycle as each blade. The heart and soul of the whole blade assembly process is, of course, the curing oven. Here we built an addition onto our machine shop just for this process, which houses the curing oven, the etching process, and related activities. This entire system was built around the adhesive, basically to meet the requirements of a 270-degree cycle for a 60-minute soak time, clamped at 50 psi with a 1 degree per minute rise rate. It's built upon a rigid stainless steel frame. We designed and made all the internal components in-house, including all the air cylinders that apply the clamping pressure for the adhesive. There are 32 individual air cylinders under this oven. Since the leading edge has a wider adhesive strip and more surface area than the trailing edge, a greater clamp force is required. The cylinders are sized accordingly, and their air pressure is controlled precisely. The other major consideration in the design of the curing oven is thermal expansion. From ambient room temperature to cure temperature, a 12-foot blade will expand almost 300 thousandths of an inch, or 7.5 millimeters. Because of this, only the center is rigidly mounted to the frame, while the outer sections are allowed to float in some slides while the material expands as it heats up. The parts in the oven are made from the same alloy as the blades, so they have the same coefficient of thermal expansion. And during the heat cycle, everything expands and contracts together evenly, removing any chance of any shearing forces acting upon the adhesive bond. Applying a twist into a set of gyro blades can have some very desirable effects. Among these is a more even distribution of the lifting forces along the span of the blade, and a reduction in the size of the stalled region at the center of the rotor disc, among other things. Other manufacturers in the past have imposed a twist in their blades by simply twisting the entire clamping section of their oven. We've taken this quite a few steps beyond that by actually 3D machining the true airfoil shape with the twist right into the inserts of the oven. Therefore, we can change the airfoil shape, we can change the amount of twist, and the location of the twists, all by simply swapping out these inserts. Razor blades feature a non-linear positive twist of 5 degrees. Non-linear meaning the increase of the angle of attack does not progress evenly from the root to the tip of the blade. The first 2 degrees of twist happens in the first 30% of the blade, with the final 3 degrees slowly diminishing as we progress out to the tip. This has required a lot of design and manufacturing efforts, but it results in some wonderful performance. The entire oven is well insulated to control the heat within. The hood of the oven is divided into 2 cavities. The upper cavity is for the heating elements and to keep them isolated from the product. This acts like a convection oven, with air being drawn up in the middle, passed through the heating elements, and then directed down on the ends with a constant air motion to heat all the components evenly. We're monitoring the temperature with temperature probes in 3 locations to assure accurate readings. The hood opens up to allow access inside the machine. The blades are then placed into the clamp mechanism, which contains the machine profiles. A little silicone-free parchment paper will protect the adhesive from getting on the clamp inserts. You'll see a little jump right there as the twist is imposed on the blade. The trailing edge is then clamped, pulling all the components into precise alignment. End clamp is then added to hold the top and bottom skins to the end caps, and the curing process is ready to start. The control system on the oven automatically runs a heat cycle, as well as the collection and saving of the data with every set of blades produced. Here you can see the output on one such cycle. The cycle begins with a 1 degree per minute ramp up to the soak temperature. That's followed by a 60-minute soak at prescribed temperature, which is 270 degrees for this adhesive, followed by the cool down phase. You can see with the well-insulated system, the cooling progresses slowly until we reach a safe temperature, where we can raise the hood of the oven and then the temperature drops off rapidly after that. As mentioned earlier, a set of coupons is made with the same materials and adhesive and processed in the same etching and cure cycle as the blades. The first process is to check the integrity of these coupons to assure the adhesive is working properly. In a peel test such as this, we are looking for PIW, or pounds per inch of width, for a peel strength of the bond. During this process, we are looking for adhesion and cohesion, meaning the bond of the adhesive to the aluminum base, as well as the adhesive to itself. With the coupons confirming that the cure cycle was successful, the blades can be removed from the oven, and we can add the holes that will allow the blades to be attached to the hub bar. Now we can move on to the polishing phase. After light sanding and then progressing through a series of polishing compounds, blades end up with a beautiful, smooth luster. We currently produce 11 and 12-foot blades. Combining these with a 1, 2, or 3-foot hub bar allows us to provide rotor systems ranging from 23 to 27 feet in diameter. The hub bar is machined out of solid 6061 T6 billet aluminum with a 2.75 degree coning angle machined right in. It's not bent. The hub blocks are also machined from solid 6061 aluminum stock. Here you can see the profile being machined onto the bottom of the teeter block, which will mate up with the corresponding profile in the hub bar itself. We'll touch more on the function of this profile later on in the video. Here you can see the finished machine components, both beautiful machined aluminum. Of course, it's the straps that join the hub bar to the blades themselves. These are in 2 pieces. We have the inner straps, or spacers. They're machined from aluminum that match the 8H12 profile of the blades. There's a separate one for the top and the bottom. The profile hugs the airfoil exactly and provides a perfect match against the blade with no pinch areas or gaps. Those are then topped by some 3/16 80,000 psi steel plate straps for fatigue resistance. The inner aluminum straps are anodized, and the outer steel straps are zinc plated to protect against corrosion. All the hub bar components are assembled on the bench, and then the unit is moved over to our assembly stand to connect it to the blades themselves. Here we have all the AN hardware readily available and clearly marked. Also in this area are the assembly instructions, including the AN torque values. The first step in blade calibration is the blade stringing. We use a method where we support the hub bar, much like it'd be mounted onto a rotor head. The ends of the blades are supported via cables mounted above. These are precisely plumbed to the end of the blade, and they hold the blade in a very natural position without applying any side forces or twisting of the blade. The end caps of our blades feature a nice little machine groove for alignment of the string during this process. The alignment string is then stretched to the length of the blades, and the string naturally falls into these alignment grooves. The string can be weighted or clamped to make it taut and secure as it passes above the registration mark on the teeter block. Our system allows the ends of the blades to be raised or lowered until the string just floats above the registration mark for precise alignment. With the blade alignment now set, the strap bolts are tightened to secure the blades in position. The balance of the blade set is checked against a calibrated scale system. Weights are added to the blades until we have them balanced to within 1 gram. Any adjustments needed are performed by adding lead weight into the balancing cavity at the tip of the required blade. The next step to calibration is to ensure that both blades are running in the same plane. We do this with blade tracking. This is performed on our test stand. To view the blade position, we use LED lights on the blade tips, which are much more visible and accurate than a reflector system. These are bolted to the tips of the blades, and they're brought up to a test speed and monitored. Now please note this is not in any way a true representation of the forces that the blades will see in flight, but it is a very good starting point to build upon to assure the smoothest performance available. One of the best features in razor blades is the adjustment method for tracking. This is accomplished with the radiuses on the hub bar and the teeter block you saw being machined earlier. Any adjustment in tracking will pivot the blade assembly at the center of the teeter bolt hole, so the CG remains in the same position, retaining the chord-wise balance of the system. This is allowed by a little counter drilling on the inside of the components for the fastening bolts. Here's an animation showing a much exaggerated motion of how jack screws can push the teeter block back and forth. This will in turn add pitch to one blade while reducing the pitch of the other blade. If you need to increase the pitch or the fly height of the X blade, just simply loosen the bolts a little bit, give the X screw a quarter turn or so, retighten the bolts. Just that simple. On other systems, you'll have to adjust the tracking by using shims between the hub bar and the teeter block. Although this works, it's certainly not an elegant solution. Just for reference, 1/8 of a turn of the set screw would equate to adding a 3,000th shim on other brands. A shimmed assembly will also result in the force being spread across just two thin lines of contact between the teeter block and hub bar, whereas the razor blade system retains full surface contact between these components regardless of the pitch setting. Once all the calibration is complete, it's time to load them up and take them to the airfield for testing. We do the testing on our own GT VX series gyros, Dominators, Air Commands, and others. This video shows the result of the first flight tests with a set of 25-foot razor blades. Now you can see the amount of stick shake here. This is with the blades just out of the box per se, with the only calibration I showed earlier performed in this video. No additional dynamic balancing has been done at this point. We used to test fly every set of blades produced. However, we discontinued that process. Quite frankly, after testing many of our blades, we never found any inconsistencies. Now, if you want a peace of mind that your blades fly well, then by all means, just ask us. We'll take them for a spin before we box them up. We'll be happy to do so. A very well-built shipping crate is included for each set of blades at no additional charge. Covered in plastic sleeves with vent holes, the blades are cradled in custom-cut foam inserts to lovingly cradle them. The hub bars are secured on their own crate with hardware and instructions. The crates are banded together and ready for the truck. When not being used for blade tracking, our test stand is used for non-destructive fatigue testing. We have actuator plates that bounce the blades up and down while they're being rotated. Typically, we run about 1,000 hours, stopping every 100 hours to clean the blades and inspect for any potential delamination of the adhesive bonds. Of course, any set of blades subjected to this test is never to be used for flight. There are some types of forces that the blades will never see during a typical flight, but some destructive testing is a good idea to prove the bond strength of the adhesive. Here you see a sample that we subjected to the hydraulic press, bending it in every way possible, resulting in catastrophic failures of the leading edge, extrusion, and the skins. But you'll see between these fractures there's no separation of adhesive or delamination of skins in any location. We keep blade components in stock and ready for final assembly to customers' requirements. From order time to shipping is typically less than 2 weeks. Collectively, our blades in service have accumulated thousands of hours of flight time with glowing reports. I'm proud to say that razor blades have been issued a Section T approval by the LAA CAA for use in England. Our products are available for UK and European countries via our distributor, Phoenix Aero in Cornwall, England. We are currently working towards ASRA approval for both of our rotor blades and our gyro kits for our friends in Australia. We take great pride in our entire product line and will never give the customer any less than our absolute best. Thank you. To this presentation of razor blades rotor systems. I'll try to cover every aspect of the manufacturing process so you can see just how far we strive to create nothing but the best stuff.